Okay, so we're up. So Monday morning, it's always fun. Weather's getting better, so it's always nice too in Florida. So we've done a lot. If you go through the chapters, chapter 2 was a lot about coordinate systems and how to relate them. And if we know a point, for example, in coordinate system B, how do we calculate it in A? If we know a direction vector in B, how do we get it in A? It was all that kind of stuff. We did a general problem. B was aligned with A, and we rotated about some unit vector M by an angle theta, and we were able to get the rotation matrix. So we have a lot of tools at our disposal. And then in the following chapter, we went ahead and we looked at what happens when I take a robot out of the box when I buy it for the first time. We need to make a kinematic diagram and label all the S and the A vectors, and then jot down in a table based on your choice of S and A vectors, what are all the constant mechanism parameters. So for all the links, you're going to know the alphas and the A's. Right, the twist angles and the link lengths. And depending on the joints, you'll know certain parameters. For example, a revolute joint, you'll know the joint offset value. Then we said, once we label all our S and A vectors, let's attach coordinate systems to all the links and do it in a very systematic way. So what we did, for example, on link A12 is we put the origin of its coordinate system at the intersection of the S1 line and the A12 line. We put the Z of that coordinate system along the S1 and the X along A12. We did that for all the coordinate systems, and that way when we looked at what's the transformation matrix, for example, 2 to 1, 3 to 2, they were all the same exact format, right? For coordinate system 2 is aligned with 1. We translated A12 along the X, rotated alpha 12 about the X, translated S2 about the new Z, and then rotated theta 2 about that new Z. And that got us the 2 to 1 transformation matrix, and then they were all the same format because they were all attached in the same manner. And then we put that all together in the chapter that I did on the video, because I think the chapter was only like 7 pages, but it was about the forward analysis. So what's really important for us is that there's no ambiguity. So we took the robot, labeled the S and A vectors, wrote down our constant mechanism parameters, made whatever free choices we need to establish the A67 line. Usually it's etched into the mounting plate. And then we said, once we've done that, we have all our constant mechanism parameters, we said, given the variable joint parameters. So if they were all revolute joints, it was phi 1 through theta 6. And we wanted to know where's the end effector. And it turned out that it was pretty much just multiplying T1 to fixed times T2 to 1, 3 to 2, and that basically solved the problem. So before we jump into the next chapter, one comment I wanted to make was, we always talked about on these pictures how it didn't matter if somebody else pointed the vectors in the other direction, they're still going to get the same results for the forward and reverse analysis. So for the person that labeled everything like this, let's look at the A12 and let's label theta 2. So they would say that theta 2 says put your thumb of your right hand along S2. I'm going to draw this dotted line parallel to A12. And then sweep your fingers from the A12 direction to the A23. So that's what they're going to say, theta 2 is. So they have their constant mechanism parameters, they have theta 2. So what happens if another person went ahead and pointed their A12 in that direction? Okay, if they did that, then their A12 value is going to be a negative of, I'm going to say the first person is the green person. Right, because to get from the 1 line to the S1 line to the S2 line, I'm walking now in a direction opposite to what we chose. So, okay, so they're going to have a negative value for that. So you look at their mechanism parameters. And then at first you say, well, how are they possibly going to get the same answer on the forward analysis? Like, basically, I want this 6 to F. Well, let's look at what they're going to report their theta 2 is. They're going to say, hey, the robot's in the exact same position. And I'm going to report theta 2 as the thumb of my right hand, along S2. And I'm going to draw this dotted line here parallel to the current A12 direction. And I'm going to sweep my right hand from here all the way around there. So the person that pointed the A12 in the other direction is going to say, well, obviously at this instant in time, the theta 2 value is different than what the first person had. So what happens is when the purple person takes their negative value here with this different value of theta 2, and they do the whole forward analysis, they're going to determine that the 6 coordinate system is in the exact same place. So that's a little bit of a story. I should have multiplied it all out and showed it all numerically, but that's why when you pick your S and your A vectors, it doesn't matter which way you point them. Just make sure when you write down your table of values, it's according to your direction. And then in this case, on the forward analysis, the blue person says, well, theta 2 looks like about 60 degrees, and the other person says, no, it's 240 degrees, and they're both right based on their drawing. At that instant, that is what theta 2 is doing. And when they calculate where the tip of the robot is, they're going to get the same answer. Okay, so I want to make sure I told that story. So we're actually going to go into chapter 5. So the danger is that the first exam, I think, is the Friday the 27th. So it's like a week from this upcoming Friday. So there's kind of a tendency to say, well, if the exam is really covering up through chapter 3, but I mean, chapter 4 is nothing more than chapter 3, but I will limit it to chapter 3. If the exam is through that, then why am I going to listen to chapter 5 now? I'll catch up on the videos later, right? So it's kind of natural to do that, but it's a little dangerous so too. But so I really can't just wait for you to get those homeworks done and then, you know, and then have the exam. We're going to have to dive into chapter 5. So chapter 5 is going to be the start of doing the reverse analysis. And we're only into mid-September, so we haven't been going that long, and yet, right, that's one topic left, right, reverse analysis. So it's going to be a long one. And I actually want to make sure I look up what's the title of this chapter. So I have a crummy version here. So let's pull that up. Oh, it's the problem statement. Okay, so we're getting ready for the reverse analysis. So again, what's super important is that there's no ambiguity. Right, that we tackle this and there's no question what we're given and what we're looking for. So I'm going to go ahead and just do it off the PowerPoint instead of writing on the board right now, but let's look at what we're given. We're going to be given, again, for our manipulator, I call them all the constant mechanism parameters. So if you had a 6 revolute, which is kind of common for a lot of these industrial robots, then you would know for those links, 1, 2 through 5, 6, you're going to know the link lengths and the twist angles. And because they were revolutes, you're going to know S2 and S5. And you say, remember, there was no S1 because the fixed coordinate system origin is at the same. And there's really no S6 that's a constant that never changes, because S6 would be how far do I walk along the S6 vector, which I can see, from the A56 vector, which I can see, to get to the A67 vector, and there is no A67 because there's no S7. So we get to pick that distance to decide how far we walk out to where the A67 vector will be. And then we're going to etch a direction, usually in the tool mounting plate, and say you are A67. So basically, we have to establish that coordinate system attached to that last body. So what's going to be different this time on the forward analysis, this was up here and that was down there. So what we're going to say now is, well, hey, there's a tool point in the known in that last coordinate system, and I'm going to specify this is where I want that tool point to be in the fixed. And remember, the fixed is origin is back at the intersection of the S1 line and the A12 line, and the Z is along S1, and the X and Y are fixed to ground. And I'm going to say that is where I want the tool point to be in that fixed. And this is the way I'd like those two vectors, that's the Z and the X axis of the 6 coordinate system. That's the direction I want them to be pointed in the fixed. And again, if it was 6 revolutes, then it would be find the 6 joint angle parameters that'll make that happen. So it's going to be a lot harder problem. When we did the forward analysis, right, this was up here and this was down here. Given those joint parameters, there was one answer, right? The robot's in a place, and I'm going to tell you exactly where that place is. What we're going to find on this one, though, is that when we say this is where I want the robot to be, position orientation, there's going to be multiple answers. And for this 6 degree of freedom or 6 degree of freedom robot, the max answer, there could be up to 16 different answers, right? That's going to be the most, so it can get complicated. Okay, so with that, are you okay? And he's like, exactly, what are we given? And of course, this was all based on your choice of your S and your A vectors, right? Once you picked those, then you could write down your A's, your alphas, your S2s through S5s. Establish that coordinate system. There's some tool point that I know in the last system. This is where I want it to be, and that's how I want the 6 coordinate system to be oriented, by giving you the Z and the X. Okay, so Dr. Duffy came up with a way to attack this, and that's what we're going to do in this chapter. So if you look at the title of the chapter, Reverse Analysis Problem Statement, well, that's it, right? That's the problem statement. But he came up with a way to attack this. And the first thing we're going to do is that we're going to take this information and we are going to find out where 6's origin is in the fixed. Because if I can do that, then I know this matrix. I'm going to say I have a desired matrix, right? Because I know the bottom is 0, 0, 0, 1. If I can find that, that goes in the fourth column. And I've already got that in the third column, and I've got that in the first column, and the y is just z cross x. So hey, if we can get 6's origin in the fixed, then basically I'm going to get rid of this tool point junk and not worry about that anymore. So what we're saying is that if we can find that, then if I can get that location correct with that orientation, then that tool point is going to be at the desired location. Okay, so that's going to be our first step. And, oh, here's our S and our A vectors and our fixed coordinate system. And here's our, you know, I don't know why I showed that. Oh, I'm going to tell that story later. I got out of order. Okay, so what have I got in this picture? I'm showing this is where the desired, you know, tool point in the fixed is. So I'm given that, right? That's one of our given things. I know I'm given this in the fixed. So I know this in the fixed, right? I'm given what I want that to be in the fixed. So I know the, right, the x, y, z of the fixed. Okay, another thing we were given was I got my stories out of order here, but we'll tell this one while we're onto it. I'm given the tool point in the 6 coordinate system, and I'm going to change color because I can see it. Right, and here I am. I like to stand on the x-axis. I'm the observer. And I'm given the tool point in the 6th, and according to this figure, oh, come on, I did not mean to do that. Okay, it is B1, B2, B3. Right, those 3 numbers are given. And they're going to have units of length, like inches or meters or feet or something. Okay, so I look at that and say, wow, I know a lot of stuff. I know the desired where I want the tool point to be. And I know, oh, I can see them here. Here, B1 in this picture is a negative number because look at it, the point is opposite, but that's okay. I know that number. And oh, B2, oh, it looks like that's going to be a negative number in this picture also, but that's okay. Looks like B3 will be a positive number, but I know those numbers. So what I want to do is find that point right there. I want to get 6's origin in the fixed. So, you know, it's pretty much going to be easy. What if I take, okay, 6's origin in the fixed? So I'm going to take this, which is, you know, given. That's where I want that to be. And I'm going to subtract the distance B1 along the x-axis. And I'm going to subtract the distance B2 along the y-axis. I'm going to subtract the distance B3. And if I look at everything on this right-hand side here, that's all known. Right? Because I was given in the problem statement where I want, oh, I'm sorry. I was given in the problem statement where I wanted the tool point to be in the fixed. And then I knew B1, B2, B3 because you told me where the tool point was in that last coordinate system. And yeah, if I back up the B1 distance along the x and the B2, I back up along that, so that's what the negative is along the y, and then the B3 along the z, I get back there. And hey, I know those in the fixed because I was told the desired orientation of those, and of course the y is just z cross x, so I can calculate that. So right off the bat, we're going to be able to get rid of this tool point thing, and I might as well say the problem statement was, if I was to go back a couple slides, I could go back here and say, for this, I could say I'm going to give you this and get rid of that altogether. So here what I'm saying, given all the constant mechanism parameters, I established that last coordinate system. Here's where I want that last coordinate system to be, right? Because the fourth column we just calculated. And then the other columns, you know, were given when I said S6 and A67. Find the joint angles that'll make that happen. Okay. So how can we attack this problem? So here's what a lot of people do on this problem is this. They come up with this iterative solution technique. So they know right off the bat that they have one true equation. So they say, and at this point, I know what I want that to be, right? Because we got rid of that tool point thing. We backed up and got 6's origin. So that equals that times this times this, times this, times this, times that. And I'm using the 6 revolute as an example. So you know they have a true equation. Can we use that in the forward analysis? It turned out on the forward analysis, everything on the right-hand side was given. For the reverse analysis right now, this thing has the angle phi1 in it. And that's all that's in it. Remember, the first coordinate system and the fixed system have the same origin, and the difference was the first was rotated about the z by the angle phi1. This one had, what, A12, alpha12, S2, and theta2. Theta2 is the only unknown in that one if they were revolute joints, which I'm just assuming for now. And this one has the only unknown in it. So in an iterative solution, what happens is I have a desired matrix over here. I know where I want 6's origin to be, and I know how I want S6 and A67 pointed in the fixed. And they've got this equations. What they do in an iterative solution, you make a guess for all 6 angles, multiply it out, and see what you get. So I'm going to say over here, I've got my desired matrix, and I do all the, I make my guess, and I'm going to get 6 to F, and I'm going to call that the guess. You say, gee, was I lucky enough to get the same, as the desired? Odds are you're not. So what do is you make a new guess on all these joint parameters, see what you got, and see if it equals. So it's like a trial and error thing. But in these iterative solutions, they have these techniques where if I make my first guess for those joint angles, and then when I make my second guess, I can kind of guess in maybe the right direction, should I say? I don't want to call them intelligent because that's not right, but there are algorithms that'll try to make your next guess based on what happened on your previous guess, try to make the next guess a better guess. And eventually, you hope in this, they call it converge, right? You'll get a set of answers here that'll do it. So a lot of people will do that, but there's kind of an issue with it. And the issue is that I mentioned there could be up to 16 possible cases. So there could be an A case, and there could be a B case. And all these 6 angles here are going to be different than those, and there could be up to 16 of them. When you do this iterative technique, it is going to, say, converge to a solution, and it's going to be, if there are 16, it's going to be one of the 16, and you don't know which one. The one that it goes towards is going to be based on what was your initial guess of all these parameters. So I make a different initial guess, it might converge to the C case. And I make another guess and it converged to the A case. And I don't like that. So I would like to, and this is what we're going to do in this class, is for our problem statement, if there are 16, I'd like to get all 16, and then I can pick the one that I want. So that's what we're going to be doing. So kind of a quick thing about their iterative. I took a class from Dr. Sander. George Sander was an excellent designer, and he went through all these iterative type techniques, and they're really cool, but we're not going to do that. We're not going to do that. Okay, so that was a story I was supposed to tell earlier in the PowerPoint that I got the order out of order, but you can kind of see the iterative thing is kind of weird. Okay, so back on the PowerPoint, this is what we'd already talked about. If I took the given where I want the tool point and the fixed, what I mean here is that's the first element of that vector, which is B1, so I go negative, that okay. So I know that, so we now know that, fine, fine, fine. Okay, so here's what Dr. Duffy came up with. He said, let's look at this manipulator. We're pretty much looking at, I call them 6-degree of freedom manipulators, so we ought to talk about mobility for just a second. If I take 2 bodies, I think this story probably comes in a different chapter, but I'm going to go ahead and tell it now. Say if I got these 2 bodies, say how many parameters do I have to know to tell you exactly where both of these bodies are? So each of these bodies will have a coordinate system attached, right? It took 6 parameters. So if I look at n bodies then, I would say if I had n bodies, what would be the mobility of the system? It would be the mobility 6 times n. So, okay, because I got n, none of them are touching each other. And then we're going to take one of these bodies, though, because the robot has one of the bodies bolted to the floor. So we say that one has 0 freedoms. So I'm going to say right now I have n bodies. 1 is grounded. If I look at that whole system, so none of the bodies are touching each other, it's just one of them is bolted to the floor. And then we introduced these joints, and when we looked at the simple joints, we said that a revolute joint allowed one freedom, and a prismatic allowed one freedom, and let's see, a cylindric allowed two freedoms. So I'm going to let, for joint I, let that represent the relative allowable freedoms of joint I. So it's probably going to be, F sub I is going to be a 1 or a 2, basically, because it's either a revolute, a prismatic, or a cylindric is how we're going to model things. Okay, when I take two bodies then, so before they're connected, I had 6 freedoms, 6 freedoms. Say I connect it with a revolute joint. I got 6 freedoms. I only have 1 because of the revolute. Right, I needed 6 to get this body, but for this body now I just need 1 because it's the only freedom that it has. So what that joint did is it took away 6 minus Fi. So I'm going to say I have J joints. So it looks really terrible, but what I'm saying is if I have N bodies, one of which are grounded, and I have J joints where F sub I is the freedom of joint sub I, then I could say this is the mobility of our system. So if we look at the robots that we've been doing, and they've got, revolute, I'm just going to go with the revolute joints, but we had 7 bodies, one of which connected to ground. I had, 6 joints. The F sub I is 1 for all of those. So let's see what this equation comes out with. It better come out with 6. Okay, I've got, each joint had 1 relative freedom. So each of those revolutes took away 5. So it looks like I got 6 times 6 is 36. I've got 5 6 times. Yeah. So nothing really surprising here, right? We've got the 7 bodies connected. I did 6 simple revolute joints. In the mobility, the entire system is 6. And the reason industrial robots have 6 joints is because I would love that end effector to have 6 degrees of freedom so I can put it anywhere I want to within the reachable workspace. So it kind of makes sense. Okay, so now what we're going to do is say, imagine that I have, it's a closed loop mechanism. So I start with my N bodies, and I'm going to go ahead and I'm going to, I'm actually going to introduce an extra body. I'm going to say, I've got 7 bodies now. I'm going to go ahead, and one of which is fixed to ground. Let's see if I don't mess this up here, because I know I need the answer to come out. Oh yeah, so I've still got 7 bodies, one of which is connected to ground. But now I'm going to have 7 revolutes. So what we have is, I've got a picture in another chapter, but I've got this link that's fixed to ground, and then there's going to be this other link. I'm doing a terrible drawing. And I go all the way around, and then finally it connects back up here. And so it's a closed loop mechanism. One of the links is fixed to ground. And I want to go ahead and get the mobility of that thing. So what's happening now is it turns out that right, I've got 7 revolutes now. I'm going to close it. I'm going to imagine that they're all revolutes. So I still had 7 bodies, one of which was fixed to ground. Da, 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 da. So if we were to add this one extra link and close it back to ground, we're going to get a 1 degree of freedom device. And that's going to be kind of important to us. I'm kind of worried if that story didn't make a ton of sense. Don't worry, okay, because it didn't come out as good as some other years. But we started out with this open loop robot that had 6 degrees of freedom. If I was to add 1 more body connected back to ground, I'll get a 1 degree of freedom. So we're just going to tuck that away and say, well, I don't know why that story was told, but there is something that's going to come of it. So here's what Dr. Duffy came up with. He says, here's my picture now, and I look at my reverse analysis and what I'm given, and I can see over here the fixed coordinate system, right? And the Z is along there, and I just drew the A12. I didn't bother to draw the entire robot. I just said, hey, I know where this is now, all in the fixed, right? 'Cause we just did that. We got where 6's origin was in the fixed. We were given the desired direction of that and that in the fixed. So I can visualize that. So what Dr. Duffy did is he said, let's go ahead and pick a couple of parameters so that we can establish an S7 line, even though it doesn't exist. So we call this like a hypothetical S7. And all I know is that the S7 has to be perpendicular to A67, and I can see that. So here's what we decided to pick. We could have picked any two things, but having zeros on our equations are nice, and having 90s for angles are nice because sines and cosines go to zeros and ones. So we picked those. He said, you know, if I picked that, can I visualize the S7 now? Well, yeah, I walk no distance along the A67 to get from no distance along A67 to get from S6 to S7. So what that meant is this S7 line that we're trying to establish intersects the S6, so I can see the line. And when we picked 90, I put my thumb of my right hand here, and I spun from 6 to 7. So yeah, if I make those two parameters, I can see that line in my head because it doesn't really exist for our robot. And we picked the A670 and the Alpha 6790 just because it makes some calculations in the future kind of simple. Then what he did is he said, you know, I can see this line. Definitely can see the S1 line, right? That's along the Z of the fixed. Any two skew lines in space are going to have a unique perpendicular. So he says, okay, once I made those to see the S7, I would love to get all the parameters associated with that unique perpendicular. First thing I need to do, though, is pick a direction for A71. It's going to be a unit vector. And basically, what's the direction? It has to be perpendicular to S7 and S1. Okay, based on our choices, do I know, of course, I knew that in the fixed, I knew that in the fixed. I know that point in the fixed. Do I know this in the fixed? Yeah. Turns out to be the negative, the direction of that because of our alpha. So I know that in the fixed. Do I know S1 in the fixed? Yeah, 0, 0, 1. Hey, I'm going to do this. A71 in the fixed. I could go S7 cross S1 and then unitize it. Or I could have it S1 cross S7. It's my choice. So I'm going to pick one. I'll probably pick that one in the book. So yeah, I now know this, what I chose for that. Okay, now the picture's kind of messy. I'm going to change color here. Our goal in this chapter then is to determine 6 numbers. Based on our choice of that A71 vector, can I get 3 distances and 3 angles? Can I get that, that, and that? Oh, look at, there is an S1 now. How far do I walk along this to get from the A71 line to the A12 line? Okay. 3 distances and 3 angles. And the angles are going to be this, this, and then this weird one over here that we're going to talk about in a second. And kind of the goal of this chapter is given, you know, what we're given is the reverse analysis problem statement. We went and calculated 6 origin in the fixed. We're going to make those choices. We're going to calculate those 6 numbers. And that's what this whole chapter is about. Why are we doing this? Okay, if you look at all these dotted lines that I've got drawn on top of, once we picked our S7 direction in the fixed, we've added a hypothetical link to the system, right? I got the unique perpendicular. And for that hypothetical link, I know it's alpha and I know it's A. And then I look over here and I'm able to get theta 7. And what we've done is we've taken our open loop robot that had 6 degrees of freedom. When we add this hypothetical link and I calculate all these parameters, because I know the stuff about the hypothetical link, the A and the alpha, what we've done is we've turned our open loop robot that had 6 degrees of freedom into a closed loop mechanism, which has 1 degree of freedom, but I know theta 7. I have a 1 degree of freedom device where I know one of the thetas. We should be able to solve it. And this is what Dr. Duffy did for all of these robots. We're going to turn these open loop robot problems into 1 degree of freedom closed loop mechanisms. So again, this chapter is just what's in that red box down there. I need to erase all the junk here. But this chapter kind of can get lost a little bit because basically we're just saying, you know, given this and the fixed, make some free choices to see this line and then calculate those 6 parameters. And it doesn't really explain the great, why are we doing that maybe, or all that kind of stuff, but it just says that's what we're doing. But the reason we're doing it is we're taking our open loop robot that had 6 degrees of freedom and we're converting it to a closed loop spatial mechanism, which is going to have 1 degree of freedom. So if I know one piece of information about that 1 degree of freedom mechanism, I can solve it. The one angle we know is theta 7. We're going to know that when we close the loop. So this whole chapter is about close the loop. And then you're going to have a homework coming up to write a function again. And it's important to be a function because you're going to be calling it in future programs. But we'll see what the setup is. But the setup is basically given T6 to F, calculate these parameters. There's a function that does that. Okay. So I don't know if the stories are coming out as good today. This was pretty clever. What he tried to do was come up with a unified way to attack these problems. And this is kind of the start of it. I'm going to turn all of these open loop robots into closed loop 1 degree of freedom mechanisms, and then work on solving 1 degree of freedom mechanisms where I know one piece of information. I got to hit down. Okay. So how are we going to do this? So let's put what's given and what we're looking for. We got 20 minutes left today. I'm just going to say that. And I don't even care what kind of robot we got and what the constant mechanism parameters are right now, because that picture I had where I didn't even draw the robot, it's like, I don't even care now. Given that, we're going to go ahead then, and I'm going to put under the given, we're going to choose this distance, and I guess I was 6, 7. I'm assuming there were 6 axes in the robot, and da-da-da. And I'm going to choose that is 90. So given where I want that last, the coordinate system attached to the last body, which is usually the mounting plate of the robot, and I'm going to make those choices because now is known. I guess I'm still kind of putting this under the given category because then I have to go ahead and choose my A7 one direction. So I'm going to choose it as, I'm going to go S7. It could have been the other one. If I choose the other one and then we're one of our 6 distances, one of our 6 things is A7-1. If I choose the other one, the person's going to get the A7-1 with a negative value, whatever the first person got, and they're both correct. And their alphas are going to be different. That's all good. I got to unitize it. So I'm dividing it by the magnitude of whatever that was. Okay. I think I got everything there. 3 angles and 3 distances. So the distances, and I'm going to go like put these little marks on them to make sure they're a capital S. I want to get that distance. Well, there is an S1 that I can see now because how far do I walk from the A7-1 line, which is the unique perpendicular between this new S7 line and the S1 line? How far do I walk along S1 to get from the A7-1 line to the A12 line? In 3 angles. Oh, let's go ahead and look at this thing I'm calling gamma 1. We're going to get it, but why is it useful? Why is it useful? So if we go back to this picture, let's see. Let's draw theta 1. Oh, let's draw phi 1. I'm sorry, phi 1. Based on this picture, boom, right? It was the angle from the x of the fixed to the A12. Okay. It looks like, I'm going to change color here. I drew this line here parallel. And I know what A7-1 is. I chose it so I can see that direction. And gee, would there be a theta 1 now? Yeah, theta 1 would be put your thumb along S1, sweep from the A7-1 direction to the A12. Wow, look at what gamma 1 is going to do. Gamma 1 plus phi 1 is going to equal theta 1. So I could say phi 1 is equal to theta 1 minus gamma 1. Okay, so why? We're going to get gamma 1. It's not going to be hard, but why do we care? It's because when we do our analysis of this 1 degree of freedom closed loop mechanism, we're going to calculate, theta 2 and 3 and 4, but we're also going to calculate theta 1. If I tell the robot to get to where you want to go, make theta 1 equal to 30 degrees, the robot's going to look at me like I'm nuts because it says, well, I don't have any A71 reference. I only know the x-axis. So when we do our closed loop mechanism, we are going to calculate theta 1. But because we know gamma 1, we're going to be able to convert it. We're going to be able to tell the robot that you need to have your first angle to be phi 1 of such and such. And the robot's going to say, yeah, that's cool. I know what phi 1 is. So that's why gamma 1 is going to be important. Because when we get into the closed loop mechanism, we're going to calculate theta 1, but that's okay. So that's why it's important, but then we have to get it. So I'm going to peek down here. Okay. So I'm going to do it on the board instead of what's on here. Okay. Now, I can visualize the S7 line, right? We're going to go for these joint angles first, right? Theta 7, alpha 7, 1, and this gamma 1. So when I look at this picture, okay, I've picked my A7 1 direction. I know what that is in the fixed. I know S7 in the fixed. I know S1 in the fixed. Do I expect, let's start with theta 7. Do I expect there to be more than one answer? No. Theta 7 is put your thumb along S7. I've got that in the fixed. Sweep from A6-7, and I've got that in the fixed, to A7-1. I already got that direction in the fixed. There is one theta 7. What that's telling me is that I need to calculate the sine of theta 7 and the cosine of theta 7, because if I know both of those, I'll get one answer. Okay, if I go ahead and I draw the S7 vector. Okay, and I'm going to draw the A6-7 vector that's in the picture. And hey, I know that in the fixed, I know that in the fixed, right? Right, because of our choices, alpha 6-7 is 90 and da-da-da. That was given in the reverse analysis problem statement. And, oh, we already got now the A7-1. Right, because I decided to take S7 cross S1 and then unitize it. I know all of those in the fixed. I'm going to take this line and go dot, 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 put it over here. And I draw theta 7, and it's right hand from 6-7 to 7-1. Okay, if I have these two directions, so this is along the direction of A7-1 in the fixed, I need to get the sine and cosine. The first one we're going to get is the cosine, and we're going to write it like this. I'm going to say the cosine of that angle is going to be the A6-7 dotted. And if you go back to when you did your scalar product stuff in, I don't know if it was a linear algebra or a geometry or a trig class, but you get a scalar result. You don't get a vector. It's the magnitude of the first times the magnitude of the second. They're both unit vectors times the cosine of the angle between them. Is physically what the dot product. Oh, we already talked about how it didn't matter what coordinate system you did the dot product in, It's invariant with choice of code. So based on everything we know, boom, I know that. I'm going to write down how we're going to get the sine, and then we're going to go back and show that it's right. I'm going to peek to make sure I don't write this down wrong. A6-7 cross A7-1, and I'm going to dot it with S7. You say, wait a minute, that's going to give me the sine? First of all, do I get a scalar? Well, this cross product gives us a vector, and a vector dot a vector gets us a scalar, so at least it does that. Okay, when you go back to your cross products, well, what does it represent? It represents the magnitude of the first, 1, magnitude of the second, times the sine of the angle between them, times a unit vector that's perpendicular to both of those. Well, the unit vector perpendicular to both of those is that. Right, so this cross product represents magnitude of the first, magnitude of the second, times the sine of the angle between them, times a unit vector that's, okay. And then when I dot that, magnitude of the first, magnitude of the second, the angle between them is nothing, and you get S7. So we're just going to go, boom, calculate sine and cosine of theta 7. Okay, if you know the sine and cosine, most of your computer languages have a function built in called atan2. So I could say that theta 7, it's going to return it in radians, is going to be atan2. They want the sine and the cosine value, and that'll give you the unique angle. Now, it's not hard to write it yourself. You could say, do the inverse cosine and get two angles, and then you look at whether the sine is positive or negative, and it's going to tell you what quadrant it's in, and that'll tell you which of the two inverse cosines was the correct one. It's all good, but they have them built in. If you work in Excel, that's the only one I've seen where they're atan2, they go cosine sine. That's the only one I've seen is in a spreadsheet thing. But in all the other languages, I know C++, I know Python, I think in MATLAB it's got the same thing built in. So at this point, I've got 10 minutes left, I'm going to say I flat out know theta 7. Again, that's where we, reverse analysis problem statement, that's where I want the coordinate system of the last link. Made these choices so I knew that. Picked that direction, and when we're ready to go, we got that angle. We'll probably do the angles today and come back and do these on Wednesday. Okay, what about alpha 7-1? So in the picture, what have I got here? I got a mess. Oh, I'm going to erase that just because it bothers me. Where did I want to go? Okay. Alpha 7-1. Okay, I knew that in the fixed. I knew this in the fixed. And of course, I know S1 in the fixed is 0, 0, 1. Is there, there's only one answer, right? There's no way there's going to be two possible alpha 7-1s because I can see those three A71, S7, S1, and I put my thumb along A71 and I sweep from there to there. So again, we're going to get the sine and cosine. And it turns out that the equation that we're going to have for that one, I'm not going to draw the picture here, but the cosine of 7-1 is going to be S7 dot S1. Right, magnitude of the first, magnitude of the second, cosine of the angle between them. The angle between them is that. And the sine will be, again, similar to what we just had. Dot, A71. All right, because this is going to be magnitude of the first, magnitude of the second, times the sine of the angle between them, times a unit vector that's, I already got a unit vector perpendicular to those, A71. So if I dot that cross product with that, I'm just going to get the sine to come out. And again, knowing the sine and cosine, boom, I got that. And then the last angle is the gamma one, which is just used at the end to go from closed loop mechanism world back to robot world. Because the robot needs phi 1, not theta 1. And for that one, when we look at the picture, do I know that direction? Yep, A71 in the fix. Do I know that direction? Oh yeah, in the fix, it's 1, 0, 0. So, wow. Cosine of gamma 1 is going to be the dot product of A71 in the fixed dotted with 1, 0, 0. And the sine is going to be A71 in the fixed crossed 1, 0, 0. Oh, and it's dotted with, what's perpendicular to those two? S1 in the fixed, which is 0, 0, 1. So again, I can get the sines and cosines of both of those so that we know, the gamma 1 angle also. And again, one of your homework problems is going to be given this matrix, you'll have these two choices, you're going to calculate, what your S7 is in the fixed. It's the negative of the y of that. You're going to choose this, And then you're going to get the sines and cosines of those three angles and do a tan 2, and you've got those three angles. And now what's left to get are the three distances. Is this distance, and that distance. Okay, I'm going to jump. I don't think we have time to get the three distances today, but once we get those, I want to go to this one last slide here. This slide. Here's what our table is going to look like, and again, I assumed we had 6 revolutes. So on our constant mechanism parameters, right, that and that and that. Okay. We made a couple of free choices to establish the last coordinate system. I think it was that. Let me change color here. There's our constant mechanism parameters. Let's see. Alpha 6. Oh, these two. Alpha 6. No, wait a second. I'm sorry. I'm getting ahead of myself. To establish the last coordinate system, we picked that, and then we etched the direction for A67. Okay, when we did this close the loop step, let me try to find a color that'll show up here. We picked these two to establish the S7 line. Okay. So once I knew S7 in the fixed, I can see this S7 line and I can see the S1 line. There's the unique perpendicular between them, and we're going to calculate all the junk associated with that hypothetical link with that unique perpendicular. And let's circle what the items were. I don't know if the yellow, well, I'll try orange. Right, 3 distances, boom, 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 and 3 angles, boom, boom, and gamma 1. So what happens now when you look at this table is for our hypothetical, closed loop mechanism now, hey, I know all the A's from 1, 2 all the way back to 7, 1. And I know all the alphas. And assuming that the robot had all revolute joints here, I know all the S's. Right? The hypothetical joint there was a revolute. And over here, I know one of the thetas. And it turns out that this new closed loop mechanism now is a 1 degree of freedom device where I know one piece of information. It means we are going to be able to solve that for the other unknown pieces of information. So that's where we're headed with this. So it seems kind of crazy. Reverse analysis, we got rid of that tool point thing. We said, okay, you told me where the tool point was in the 6, and you told me where you wanted it in the fixed. So yeah, I can figure out where the origin of the 6 had to be. I'll just work with that. Once we got that, I could have picked different values and everything will still work out okay, but that made this pretty easy to calculate. And now I can see the line because it goes through, right? Because A67 distance is 0, the line even goes through the origin of the 6 coordinate system. And once I see that S7 in the fixed, I definitely got S1 in the fixed, I can find that unique perpendicular. Okay, we made our choice of this, and then we're going to get these 3 distances. And the reason is when we went to that table at the end, we're going to have a 1 degree of freedom closed loop mechanism where we know one piece of information, theta 7 is what I've got there. And then we're going to go ahead and attack them. So next class, we're going to show how to get these. It's not hard. And then you're going to have a homework problem, but that'll be well after the exam, to write a computer function that, given this, boom, get these 6 pieces of information. So we're going kind of down this, I'm going to call it Alice in Wonderland. She went down the rabbit hole and things were crazy. We kind of just stuck our head in the rabbit hole today because it's going to go, not crazy, but it's what had to be done to solve these problems. So how are you doing today? Yeah, more or less okay. Seems kind of crazy. This picture to me is super important. I hope I don't have a ton of junk in it right now. That picture. Because, yeah, we made those choices. I could see that line, and I definitely knew that. And there is a unique perpendicular. Yeah, I think I can do this. But the reason is that we're going to analyze 1 degree of freedom So somebody a long time ago wrote a comment on Amazon about, I don't understand, I picked up this book and all they do is talk about these closed loop mechanisms. I thought we were supposed to be doing robots. And I felt like putting a comment that says, well, you don't get it. Because you can turn every robot into a 1 degree of freedom closed loop mechanism. That's why we're analyzing 1 degree of freedom closed loop mechanisms. Okay, so we'll pick it up on Wednesday. And oh, and Friday is going to be just like this week. I'm going to make a video and post it for Friday. But Wednesday will be a normal class. Okay, see you then.